Alright, here is the solution to this problem. You need to find out the final velocity, acceleration, and time using two different methods. The first method that I'm going to use is just looking at straight up forces. And so for forces, I will draw a free body diagram of this object. Of course, we have gravity going straight down. We just call that mg, standard gravity. Force gravity, we have a normal force over here, Fn, and then we have perpendicular to that in line with our inclined plane, if my ruler will allow it, because I'm working with some stands over here, a bit of friction. Now we don't know how much friction's here, we just know that we do have enough to keep it from slipping. It'll be rotating, and those are the three forces. Now those three forces applied at their positions, you would have friction at the outer edge right here, going that way, normal force also perpendicular to that, and force gravity will go straight down. So if you wanted to solve this problem using forces, you also need to consider that this thing is rotating. So let me grab the penny that I used, and hopefully, yeah, looks, that fits right there in between all those. There we go. Oop, one more. There you go. Okay. So using the penny, the force gravity will be at the center, so down like that, mg. Your normal force goes up this way, Fn, and these are actually where they're applied, and then that force of friction would be applied over here, force of friction. So two different ways to look at it using forces for now. The sum of all forces here, remember that we do need it to be unbalanced, which means it's going to accelerate down the inclined plane. So the sum of all forces in our new x direction would be in the inclined plane is mg, this piece of it though, so your angle is theta right there, so mg sine theta minus the force friction, which again we don't know, and we're not going to say that it's Fn mu because this is static friction and it's going to scale, so we don't know exactly how much it's going to be. It's just going to be enough to keep it from slipping, and this will be equal to ma. And of course the normal force and mg cosine theta should be equal to each other. I'm not going to write that here because I don't think we're going to use it, but if we do, I'll write it again. Here we need to look at the sum of all torque. So the sum of all torque is equal to whatever's trying to twist this thing, and we're going to call the center of rotation the middle. There is another variation of the problem where you consider the center of rotation to be the edge, but that's kind of weird for physics 1. So just considering that it's rotating about its middle, friction is going to be the force that's doing that, and if you notice, friction is perpendicular to the radius, and so that is providing torque. So this torque is going to be our force of friction applying itself at the radius, and that's the only thing that's going to be applying itself for torque, because mg is at the middle, it's pointed away from the middle. Normal force is pointed towards the middle, so those can't possibly twist it, but they will try to accelerate it like over here. And that's it, so that's going to be equal to I alpha. The inertia for this problem was over here, 1/2 mr squared, so 1/2 mr squared, and then we're going to have an alpha there, because this would be torque. Let's see, how can we look at this thing? Well, I know I have acceleration, I can find the acceleration, I have some sort of acceleration there, but it's angular acceleration, and if we're talking about the edge, what I know is that the acceleration of this object as it rolls down, if we're rolling about the center, the acceleration of the spinning of the edge about itself should be equal to this, which would be the angular acceleration times r. So remember, you multiply by r to get the actual tangential quantity that you're looking for from an angular quantity. So if I rearrange, that means that a divided by r is equal to alpha, and I'm going to use it right here. So let's see, r force, there's an r there, I'm going to cancel one of those out. So force of friction is equal to 1/2 m, one of those r's canceled. Alpha is going to be a over r, which is going to cancel that last r. So the force of friction is equal to 1/2 m a. And that's going to be very useful for right here. So I'm going to bring that, drag it in, plug it in, and so my mg sine theta minus 1/2 ma is equal to ma. And if I take mg sine theta, everything has m, I could actually cancel that out too. But a half ma plus a whole ma is going to be, what, 3 halves ma? And let's divide out by the m, take those away, and I want that a right there, so let's move the 2/3 over. So 2/3 g sine theta is equal to a. So we actually solved for the acceleration just now. If we have the acceleration, then we can run simple kinematics and find out how fast this thing should be going at the end and how long it's going to take to get there. But we need to know how far this is, because that's how far it's going to be traveling. So using a little bit of trig, we want the hypotenuse side. We have h, and so I'm going to say that sine of the angle is opposite over hypotenuse. So h over, ooh, this is going to be a little weird, but I'm going to call it L. Alright? And so L is equal to h divided by the sine of the angle. And so that's how far we're going to go. Let's see, if I want to find the final velocity, I need to use the equation that does not have time in it. So final velocity squared is equal to initial velocity squared, which is 0, plus 2a, which is that stuff, 2/3 g sine theta, 2/3, so 2a delta x, or delta L, which would be this thing, h over sine theta. That's kind of convenient, so let's work this a little bit more. 2 times 2 is going to be 4, so 4, I got the thirds there, the signs cancel out, and we get gh. And that's equal to vf, so I'm going to go ahead and square root that. So that's pretty good, that's my final velocity. And to find my time, I know that if I go by the definition of acceleration, acceleration is a change in velocity over a change in time. And so my change in velocity is this. I just need to divide by my acceleration, right? Because I want that change in time. So change in velocity divided by acceleration should give me time. And let's find out what that is. So I have the square root of 4/3 gh, that's my change in velocity, divided by my acceleration, which was 2/3 g sine theta. Let's bring everything inside of the square root, and if we do that, we can square all this stuff to bring it in. So I've got 4/3 gh divided by 2/3 g, actually, well, that would all be squared, wouldn't it? Sine theta, this is where I would say, hey, just plug in numbers. And we'll just say it's t. So you can reduce that if you wanted to. We have 4/3 divided by 4/9, I guess. And then one of the g's are going to cancel out. We got a sine squared on the bottom. Let's see. If you, we'll just do that down here. Last step, I've got 4/3 gh. One of these, this g will be gone. Let me use a different color for that. That's gone. That's gone. If I have 4 divided by another 4, that's gone, and that's gone. That 3 is going to be turned into a 9. That'll be on top, right there, and that 3 will be on the bottom. So we have a total of 9 divided by 3, so 3 h over g sine squared theta, square rooted. And that should work out. Hopefully I did that math right. Wonder if I did. What if h was 4? If h was 4 and g was 10, let's see. I'm just going to call sine. So let's see. I've got 4 divided by 3 times g, 10 times 4. This is just me checking math. Divided by 4 over 9. And That'll be 100. So that's 1.2. 3 times 4 divided by 10. That'll be 1.2, so we did the math right. So there you go. Now you can just plug in whatever numbers you want, and that would be the time for you. So what did we find? Did we find A? We found A right there. Check that off. We found final velocity right there. We found T right there. So that's one method. Now let's go with another method. We can use energy, because this is basically an energy problem. If we include the Earth, we have potential energy, gravitational potential energy. And method number 2 is going to start off with energy in the beginning. And it should equal energy in the end. No force is going to take that energy away and turn it into something other than mechanical. So remember, this is not sliding friction, this is static friction. So static friction does not take away the energy to heat. A lot of people would assume that, but it doesn't. So in the beginning we have mgh. This turns into the energy at the end, which is going to be the moving translational velocity, kinetic energy, and the rotational, 1/2 I would be 1/2 mr squared omega squared. So 1/2 I omega squared. This one right here. The inertia is 1/2 mr squared, so we're just going to plug all that in. Looking at this, let's see what goes away. This turns into a fourth. M goes away, M goes away, M goes away, because they all have M. So we have G, I have H, that equals 1/2 v squared plus 1/4, right? And like we said before, the angular stuff times the radius is equal to the translational or the tangential stuff. So that'll be v squared. And all the m's have canceled out. And let's see, a fourth plus a half. Half is going to go 2/4, 2/4, 3/4. There you go. 3/4 v squared. Hey, look at that. 4/3 GH square rooted is our final velocity. And we got it right over here. And we can just run through the exact same kind of steps in order to find the acceleration in time, maybe? Let's see, can we do that? I think we do need to find the acceleration by going back through and looking at all these forces again. But here's a way to find final velocity. I think we do need to go back through the original steps to find the acceleration, because in order to find acceleration, let's see, do I have initial velocity, final velocity? Oh, I actually could have found, there, we'll do that. Final velocity, sorry about that, equals initial velocity plus 2a delta x. My final velocity is this thing, so we're going to plug that in. It's going to be squared, so I'm going to take the square root off. GH, my initial velocity was nothing, so I'm not going to even bother. Plus 2, the acceleration we wouldn't know at this point. We do know the change in x already, that's this. That's h divided by sine theta. And if we were to do the math, let's see, we can find that a, we'll divide both sides by 2, so that 4 turns into a 2, that's going to be a 2/3. And I'm going to move this stuff over, so let's see, 2/3. H's are on both sides, so that would cancel out. Write that in. G, and then we would have a sine theta there. And that works out, that's the acceleration, that's what we got over here. So 2 different ways. Last step would be to say, alright, we can find time, and our time would be our acceleration, or our change in velocity divided by the acceleration. Just like we did over here, it's the exact same step. So that should work out for the time as well. Well, that's the solution to this problem. It took about 14 minutes to record the solution. 2 different ways. You can probably try to use angular momentum as well, but I think the better ways would be either to do the torque and forces route, or the energy route. Energy route is a lot faster. So there you go.